All right, let's get started. Welcome everyone to the SNAPP seminar. We're really excited for our last SNAPP seminar of the semester, actually. So just some instructions. I think most people probably know these, but if you haven't been before, some quick instructions are that one, our seminar is being recorded. So if you don't want to be recorded, you can just turn your video off or watch the YouTube link as well. Please mute yourself during the talk, but feel free to keep your video on. And if you have any questions, you can either write them in the chat box, and I will wait for a good time to ask Ashia, or Ashia, you can feel free to stop throughout your talk as well to ask for questions. But otherwise, we'll have a longer Q&A session at the end of the talk as well. And the slides are posted on the webpage, and I will put the link in the chat box in a bit. And since, so as a quick note, to make sure I remember to give the announcement, this is our last SNAPP seminar of the fall semester. We've had a really great lineup of speakers. It's been a really fun semester for this seminar series, and we will be announcing our spring seminar speaker series on the website in a couple of weeks. So I'll mention it now and I'll announce it at the end, but we will, after this seminar today, we'll conclude the series for the year, and we will restart in the spring series on January 25th. All right, so today we're really excited to have Ashia Wilson presenting on variational perspectives on machine learning. Ashia will be joining the EECS department of MIT in the spring of 2021. And before joining MIT, she was a postdoc at Microsoft Research in New England, and also a visiting researcher at Heidelberg University. She received her PhD in statistics from UC Berkeley, and her research interests are in providing rigorous guarantees for algorithmic performance and developing frameworks for studying issues of fairness and governance in machine learning. Ashia, the floor is all yours.
Oh, great, thank you for the nice introduction. So I'll be talking about a kind of a series of work I've done, starting my PhD, kind of all the way up till now, with a bunch of collaborators. So a lot of these people come from Berkeley, and another batch from Microsoft and just neighboring universities. So great, I'm really happy to be here. So this talk will be about machine learning, and I'm going to kind of characterize or set a model for what I'll be speaking about. So I'm really thinking about machine learning as prediction-aided decision-making. And the pipeline, although this is a caricature of what really happens in practice, I think is a useful one. The pipeline of machine learning I'll be talking about is the following. So there's some sort of pre-planning step, but ultimately a data set gets gathered, a predictive model is formed from said data set, and these predictions are somehow ultimately result in some decision-making process. And of course, there could be a loop back to future data gathered and future decisions made via predictions. So as an illustrative example, I'll take the decision for who to hire. This is some task that has now folded on the umbrella of machine learning for some companies. And typically the way they pose it is they gather a data set. From said data set, they form a predictive model. And then using this predictive model, they make a decision on who to hire, perhaps via some thresholding method or what have you. And so the three parts of this pipeline that I could kind of label my work as being under is first this kind of algorithmic point of view. So what are the algorithms we use to generate these predictive models? How do we understand them from a theoretical perspective? And then how does that bleed into our empirical results? There's an inferential kind of problem baked in here. It's at a lot of stages in this pipeline, but I'm particularly interested in how does our access to finite data really inform our predictions, and how can we understand the uncertainty that comes from this empirical risk minimization step in trying to formulate our decisions. So I'll talk a little bit more about that, some work I've done there. And finally, there is this contextual problem or decision that kind of gets baked in here, which is for any given problem, we have to formulate it as a prediction-aided decision. And this will require figuring out exactly how to use our predictions in our decisions. And so I think this is where a lot of the fairness issues have arisen, and I've started, sticking my toe into that pool. So I'll try and kind of highlight some work I've done in this area as well. And so the outline of my talk will be as follows. I spent a lot of my research thinking about more variational perspectives on gradient-based algorithms. So I'll give some highlights from that, as well as where I've actually been heading recently. I'll touch a little bit more on that. Some of the work is kind of currently under development, so hopefully this will spark some discussions. I've done some work in my postdoc, in particular with Lester Mackey and Maximilian Casey on cross-validation and how to scale it to real-world settings. So I'll talk on about that work. And as I mentioned, some of the fairness work I've done, I've studied from this dynamical variational point of view, where I'm looking at how our machine learning models generate feedback loops and what to do about that to mitigate these negative feedback loops. Okay, great. So the first, I'll pause after each part, and then if there are questions, I'll take them. But this first part will concern a body of my work that has to do more with accelerated algorithms. And so as I mentioned, this first part is really about generating predictive models. And so there's been a lot of people in the area of trying to understand optimization from this theoretical point of view, and in particular gradient-based optimization, as this is kind of the common tool used in deep learning, which is really taking over the field. And if to kind of formalize this from the perspective of kind of theoreticians, a question that remains is, have we found the fastest possible algorithms for any given task? And how do we really formulate such a question? What are the variables we're considering? And can I really formulate this as, is there an optimal way to optimize? And so I'll kind of shed light on one perspective we've brought towards this, although there are others, and I'll kind of nod towards those. But I've been really focusing on this perspective of treating algorithms, discrete time algorithms, as discretizations of continuous time dynamical systems, and kind of what is the direct connection we can make here if we consider this or adopt this perspective. And this perspective is very, very old. So a starting point for us is gradient descent. One of the most widely used algorithms in machine learning is an algorithm which at every iteration just simply subtracts the gradient measured at the current iterate with a step size epsilon here. Very classically, we've understood a wide variety of convergence guarantees, non-asymptotic convergence guarantees in a wide variety of settings. So for example, if my function is convex and my step size is small enough, I can give the following guaranteed on how close I'll be to the optimizer. But kind of hidden here is this viewpoint of gradient descent as discretizing a dynamical system. The same can be said for a lot of other variants of gradient descent, like mirror descent, the proximal method. These are well understood discretizations of dynamical systems, and furthermore, their analysis very much parallels the discrete time analysis. So there's this direct connection that can be made there. And so this is done very classically by Nemirovsky-Yudin and a whole bunch of other people in optimization. There are other optimization techniques that have resisted, to some extent, this more precise connection being made. So there's a very classical algorithm called accelerated gradient descent, which looks like gradient descent, but this additional kind of extrapolation step is added at every iteration. And in various settings, particularly when the function it has some form of convexity or strong convexity, more sharp guarantees can be given on the progress the algorithm is making, and there are lower bounds to match it. And so this has been kind of this mathematical mystery for a while. And so the starting point for thinking about developing this dynamical systems perspective It was a work in 2014 by Wei Su, Stephen Boyd, and Emmanuel Candace, which basically presented or introduced an ODE, which they felt modeled this discrete time algorithm. So they show kind of that this can model not only the algorithm, but that the analysis is very similar in the way that it acts in a parallel way to the discrete time algorithm. So they introduce a Lyapunov function. I'll get to precisely what that means. But so this is the starting point for how we've been thinking through some of the algorithms under consideration. So kind of when seeing this work, one initial thought is that there are a lot of algorithms that can be said to approximate steepest descent dynamics. As I've mentioned, the proximal algorithm, mirror descent, Newton's method, there are a lot of them. And a question in the optimization space or in the optimization community is, to what extent can these algorithms be sped up, perhaps by this extrapolation step? And so here's some examples, as I mentioned, of algorithms that are steepest descent algorithms, and some of these have accelerated counterpoints. And these are typically done by people like Nesterov and people who have specialized knowledge of these tools, and pretty much in an ad hoc way. So there's a question of, can I now take, let's say, a sampling algorithm that's based on steepest descent dynamical system and speed it up via some complicated extrapolation step? Is there a way to systematize speeding up algorithms and really understand the boundaries for the types of algorithms that can be sped up? So that's exactly where we were looking at. We're trying to understand what are the underlying principles and to what extent this can be mapped onto existing methods. And then another question we looked at, and really the place we started, is the dynamical system perspective offers kind of a nice way forward, but there's a question of why that dynamical system, and is it optimal in some way? So I'm gonna talk about this question, this last one first, and then try and address some of the other questions. So this question of optimality naturally leads one to think through physics, or leads one towards physics, since variational perspectives are really kind of have been a boon in physics. In particular, if you think about, for example, a girl, she's throwing a ball. A basic E&M class will offer the following ODE, called Newton's law, for modeling how the trajectory of the ball evolves over time. Another way to describe this equation is F equals ma, where the force is given by the gradient of this potential function F, and the mass that's set equal to 1. So acceleration is the second time derivative. But another very popular technique in the physics community is to consider all the trajectories that the ball could have taken and describe the trajectory it does take as being optimal in some way. So this is that variational perspective. So in particular, an action potential is offered. So it's this minimization of this integral of this Lagrangian. And the functional derivative of this equation is called the Euler-Lagrange equation. And so this gives the stationary points for this minimization problem over curves. And so we can think about Newton's law not just as the second order ODE, but as the stationary solution to this least action problem, where the Lagrangian is given by this very classical equation here. So we have the first part represents the kinetic energy. It's the norm of the velocity term. And we have this potential energy given by the function itself. And so very classically, Newton's equation, here we can describe the trajectory of the ball as moving kind of along these level sets of states where the energy is constant. So energy is conserved in this equation. And so if you look or take the ODE that models the accelerated gradient descent, Then the Lagrangian, which gives rise to that dynamical system, is this damped Lagrangian system here. And so it looks a lot like Newton's law, except for we have this T cubed out in front. This T cubed causes the energy to dissipate, which is a good thing from an optimization perspective, because the dissipation allows the motion to stop. So if you think about trying to minimize a function, we want the motion or the trajectory the algorithm takes to essentially stop when we're at the optimum. We don't want it to oscillate. And so this equation characterizes how that motion or a desirable motion evolves. But, you know, accelerate gradient descent is way more general. As we mentioned, a lot of other algorithms can be accelerated. So we also did this for a large variety of ODEs, characterizing algorithms that can be accelerated. And from that, we introduced a more general Lagrangian we call the Bregman Lagrangian. This is called the Bregman Lagrangian because the kinetic energy is measured by this Bregman distance. So here H is a strictly convex function, and the Bregman distance represents the error in our first order Taylor approximation of H. And again, we have this damping term, F, or rather the damping term is given by T and the potential is given by F. And so if you compute the Euler-Lagrange equation, you get a somewhat complex second order ODE. So we also require that our geometry H is twice differentiable. And one of the nice things about this ODE is we can introduce a Lyapunov function. So this is a positive function, which is decreasing along the trajectory of the dynamical system. And this gives us a convergence guarantee for that dynamical system. So one of the nice things about mapping or moving to a Lagrangian perspective is you get this coordinate invariance. So it becomes a little bit easier to see how to map the concept onto different spaces. So in some follow-up work, people have introduced a PDE perspective, for example. So just looked at what naturally this Lagrangian would look like if F were a PDE and computed the Euler-Lagrange equations accordingly. So we also have kind of used this concept to generalize to some extent the acceleration phenomenon and give a much more general description of what it's doing. One description we have is the following. So one can describe acceleration a little more broadly as follows. So you take any algorithm which satisfies a certain progress condition. So this progress condition is that the function value is decreasing in a way that can be measured by the norm of the gradient to some power. So if you have an algorithm that satisfies this condition, what we call this a descent algorithm, you can already derive a fast convergence. So you know that it's going to find critical points of your function very quickly. If your function is convex, it's going to find the minimum very quickly at a polynomial rate. And if it's something called, if it's strongly convex, or even more weakly, if it satisfies the PL inequality, the Polyak-Chomsky inequality, then it'll find the minimum at an exponential or a linear convergence rate. So you take an example, so you can take an algorithm that already satisfies this property, and you couple it with the discretization of the Euler-Lagrange equation, then automatically in some of these more structured settings, you're going to find the minimum more quickly. So you can show if your function is non-convex, you'll find the critical points just as quickly. But if you are convex, then you'll find the minima more quickly. And there are other techniques as well. So there are other discretizations that give you even faster convergence guarantees. So this is a discretization, I think, introduced in 2014, the Montero-Sveiter style discretization. So they add this line search step essentially to the Euler-Lagrange equations, and you get an even faster guarantee when P is greater than or equal to 2. And essentially the analysis works by just simply introducing the Lyapunov function or the discretized Lyapunov function and showing it's decreasing. So there's a very simple parallel analysis between how these things go in continuous time and how they go in discrete time, which is kind of a very nice organizing principle for how you think through accelerating an algorithm. And so I want to give another example for how this can be useful. So quite clearly, if you have a dynamical system, one natural thought is to use more classical numerical analysis techniques, not only to shed light on what this trick of Euler-Lagrange equation is doing, but also perhaps to get an algorithm with even more desirable properties. So thing that immediately occurred to us is something called symplectic integrators. So symplectic integrators are very natural in Hamiltonian systems. There, typically the idea is to conserve the energy. And so you want an integration technique that will do that in discrete time. So it'll kind of adhere to the geometry of the Hamiltonian, and it'll be nice in that way. And so what we did is we took this Hamiltonian equation and we applied a very classical symplectic integrator and kind of just studied its empirical performance. And what we were able to see empirically is that these techniques tend to be a little bit more robust towards misspecification of the step size. So that's that plot on the right. We had the Lagrangian or symplectic integrator as compared to Nesterov's method. And we cranked up the step size for both in turn and saw that the Nesterov algorithm diverged more quickly. But in general, they had very comparable performance. So that was encouraging, but ideally, you want more theoretical results. And so this has kind of inspired a lot more work to look at other numerical analytic techniques. So my advisor has a follow-up paper, Mike and his students, where they do show that symplectic integrators do get some of the convergence guarantees, but they have to go to high resolution ODEs. And another work that I was particularly intrigued by is a work coming out of MIT that looks at Runge-Kutta integrators. So these are other numerical integration techniques that kind of have a higher order discretization of the ODE. So you evaluate the vector field at multiple points to more closely approximate the curve. And what they were able to show is that there exists this class of functions for which these numerical integration techniques are provably faster than accelerated gradient descent. So I've referred to this function class as strongly smooth. There's a technical condition there, but it's in the paper, so I'll refer you to that. I think I have it in a backup slide if you want to see. So this is very, very intriguing. And if you kind of go to the plots of their paper, this is how it works. So they gave two examples. One is this LP function where P is equal to 4. And the other is the logistic loss. And so we just kind of took their code and replotted everything. So gradient descent is in blue. Naturally accelerated gradient descent has a faster convergence rate. And then their symplectic integrator, after a certain threshold number of points, tend to drastically outperform both theoretically and now empirically. So one question we were asking when we looked at this is, can we do better with a simpler discretization? And the reason why we asked this is because symplectic integrators are nice, but as I mentioned, they're higher order. They require measuring the vector field multiple times. So they're a little more expensive. If you have cheap gradient computations, it's not too bad, but ideally you would want something kind of on the same order as the original algorithm, or accelerated gradient descent. So we were heavily inspired by thinking about, are there other dynamical systems we can discretize and get just as fast convergence guarantees theoretically and empirically? So we chose the dynamical system we had actually introduced in a previous paper, and this is based on the idea of rescaling the gradient. So this ODE is essentially gradient flow when P is equal to 2. But for P greater than or equal to 2, essentially you just rescale the gradient direction by its norm. And so these dynamical systems are nice because they actually come with fast guarantees in continuous time. You can show that the function is decreasing at a sufficient amount, and therefore you can introduce a very simple up and off function to show that it's reaching the minima faster than if you hadn't rescaled the gradient. Okay, so very naturally you look at that and you think, okay, is there a setting for which rescaling the gradient in discrete time can lead to much, much faster convergence guarantees? And as it so happens, so we're studying the simple Euler discretization of this rescaled gradient flow. And as it so happens, it's exactly this class of functions, of strongly smooth functions, for which you can show provably you get a very nice function decrease, and therefore this acceleration framework can also be applied. You can accelerate essentially this rescaled gradient descent algorithm. And so if you plot that on for the functions that they introduced, you get just the dramatic improvement. And so that was very encouraging for thinking through, okay, maybe going to this dynamical perspective can in some cases lead you to faster algorithms. So I just want to kind of summarize some of the contributions, but actually some of the directions I'm actively working on, because I think there are many places to take this work. So I'm really interested in studying discretizations of dynamical systems. And I think this Lyapunov analysis provides a very, very critical, essential tool for mapping this to other spaces and other problem settings. I think the variational perspective is very nice, although, there are a lot now of other, ODEs that have been introduced. And the question is, do all of these have a very similar variational perspective? And so I still think that there's a lot more to understand there in terms of its utility from a practitioner's point of view. But looking at the future directions, I think it's promising that using this understanding will give us a way to map these methods into other problem settings that are of importance right now. So two directions that I'm particularly interested in is geodesic optimization, or what I'll broadly refer to as probability functional optimization. And so the idea is essentially for some tiers or classes of convex problems, or non-convex problems rather, you can introduce a metric in which the function is what's called geodesically convex. And so there's a new toolkit kind of to now optimize these functions on this Riemannian manifold. So I think it's right opportunity for people in optimization to try and think through, can we build parallel techniques in this setting? It's not that straightforward, given that these geodesic distances are nonlinear for the most part, and so they're structured in a certain way. And so I've been working a little bit on these problems. And relatedly, a lot of sampling algorithms and problems with GANs are optimizing, broadly speaking, probability or functionals over these probability spaces. So Wasserstein spaces equipped with the Wasserstein 2 distance. And so there are questions there about to what extent acceleration can play a role. And I think that's a very much an open question. There have been some preliminary results, but it's still unclear. So I'll pause there before I move on to the next section and take any questions. Give you guys a tea break if you need. Let's see, I'll try and open the chat window. I'm not quite sure if I can see the chat window, so Christina, you'll let me know if there are any questions.
I'll let you know.
Okay,
there are currently no questions in the chat.
Okay, great.
Feel free to directly unmute yourself to ask any questions for those who have questions.
Fantastic.
I have a question, Christina. Can I go ahead?
Yeah, go ahead.
So you talked about accelerated methods. There's also a class of methods called adaptive methods. I mean, people use them in integrad and so on. Mm-hmm. So do they have differential equation counterparts, and can they be obtained as discretizations of differential equations?
Yeah, I seem to recall a paper that does study the dynamical systems perspective. I'm not as sure about how strong the connection is between the guarantees in continuous and discrete time. I do know that there are a couple parallel set of works that show that for stochastic algorithms, adaptivity can only help, and you can even get more refined guarantees. So I think that is a very interesting question or direction of future research. one question is, can you add momentum to these algorithms, or do they already add momentum? So I think these concepts might be actually, you might be able to combine them.
I had another question.
Mm-hmm.
So your speed of convergence depended on this parameter P. What stopped you cracking it up? Is it related to the smoothness of the function?
Yeah, so so the smoothness of the function determines P. Also, so I'll give you an example specifically. So these descent algorithms, so when P was 2, an example, here we go. When P was 2, an example is gradient descent will satisfy this property as long as the function is smooth. The gradient is Lipschitz. And for the cubic regularized Newton's method, this is where you take a step in the Newton direction plus this regularizer that's raised to the third power. This satisfies this property with P equal to 3 as long as the Hessians are now Lipschitz. So you get this kind of tiered smoothness as well as information that you're obtaining from your function, and that will give you this progress condition. So it's related to this, and then for our rescaled gradient descent, it was actually related to the smoothness more generally. So yeah, there's this relationship between smoothness and the extent to which you can discretize the ODE and obtain a convergent algorithm. I hope I answered your question. Kind of cut out there a little.
Yeah, thanks.
Okay, great. Okay, fantastic. So I'll just move on a little bit to talk a little bit about this cross-validation work and point towards the open questions we're pursuing there. So as I mentioned, we're really interested in how we're obtaining these predictive models from data sets. And in particular, via this technique of regularized empirical minimization. So minimizing an objective defined over the endpoints we've seen so far. And so one of the main problems that a lot of people study, particularly in statistics, which is my background, is how these predictive models will perform on future data sets. So this is a problem that I'll vaguely refer to as assessment. And there's also model selection problems. So in particular for regularized empirical risk minimization, that regularizer lambda is a hyperparameter. And there's questions about how do you choose that to have the best out of sample performance. And so cross-validation is a technique that has become, particularly for these low in settings, sorry, when n is small, then the amount of data points are small, it's become the de facto standard for addressing assessment and selection problems. So let me discuss, just as a reminder here, for what cross-validation is. So regularized empirical risk minimization, you take a data set and then you form an objective function, which I mentioned is the average over endpoints typically. And you minimize that, and that gives you a model. And so leave one out cross-validation, which is the type of cross-validation I'll be focusing on, although our results will extend to leave K out, where K can be anything from 1 to the entire data set, or n-1. Works by isolating a point, removing it to define what's called this leave one out objective, and then minimizing that. And then essentially what you do is you do this for every single point in your data set. So you're minimizing in separate functions, which is rather expensive. But at the end, you take an average over all these leave one out models that you have. And this average will give you a nice Monte Carlo estimate of what the test error will be. So it will give you, there are provable guarantees for how close this estimate will be to your test error. And so one of the long-standing problems is, of course, this is very, very expensive to do, so it doesn't scale well when n is large. So people have been looking at this because ideally we would use more robust techniques like this to get a good sense of what our out of sample error will be. So not just looking at a held out set, but perhaps performing kind of more intricate cross-validation methods for these large data settings. And so there have been a couple solutions that have been proposed to trying to find a computationally cheaper way of performing this approximation. And I'll categorize most of them as falling under this umbrella of optimizing an inexpensive surrogate function to our objective. So the idea being that if cross-validation entails minimizing all these leave one out objectives, perhaps we can optimize a very close approximation to these leave one out objectives, but something that's much easier to optimize and use these models instead in lieu of this other optimization problem. And one handy tool that all these works are really using to give us guarantees for how well this is going to do, we can kind of summarize in what we call this optimization comparison lemma. And informally, it states that if two objective functions are close, and one of them has some curvature around its minima, then the minima will be close. And so I'm going to give you a precise sense of how we use this to get guarantees. So there have been two main techniques people have used to approximate cross-validation. And it roughly can be summarized as performing some kind of Newton step, form started from our empirical risk minimizer. So we compute the empirical risk minimizer, and then we add to it essentially this Newton direction. So H will be this matrix, and then we'll have the gradient of the loss. And the matrix is chosen in one of two ways, typically. So one set of authors have proposed choosing this leave one out matrix as the Hessian of our leave one out model. So you have to compute this Hessian now in times, and essentially compute this Newton direction in times, and instead of minimizing the function in times. So in settings where it's cheaper to compute a Newton direction than to optimize a function, this will be much quicker. The other approximation is actually much less expensive. You simply need to compute this Hessian once for every leave one out approximation. And so this is actually going to be much less expensive. But we can think about these two approximations as follows. They're essentially minimizing or optimizing a second order Taylor approximation of our original leave one out objectives. And so the extent to which that's close, if they have curvature near its minimizer, then we can use that optimization comparison lemma to guarantee that what we end up with is not too far from cross-validation. And so that leads us to these theorems, or this kind of unifying theorem we can introduce for these approximations. So essentially, if the objective function has curvature and the Hessians of our objective are Lipschitz, this will guarantee that the second order Taylor approximation is close to the original function. Then this is a setting in which we can guarantee that the approximation to the test error found by this approximation to cross-validation and the approximation found by cross-validation will be on the order of 1 on n squared close. And so this is within the statistical level of the problem, so this is meaningfully close. So this is precisely the setting in which we can guarantee that approximating cross-validation via these Newton steps is going to benefit us, or we're not going to lose anything by doing this. And so just to kind of put this in context with what was already known, so there were guarantees given for these previous results. Some of them were probabilistic. They had assumptions that weren't necessary if you just simply lean on this approximation lemma. So we don't need the parameter space to be compact, for example. And we also don't need strong convexity of our regularizer. So we were able to kind of soften the assumptions given by previous works. So that's nice, but there are a couple other questions you can ask. So first of all, model selection is the thing that cross-validation is used for most. So there's a question of, can these approximations be used in this setting? The other works actually didn't address that, even though people persistently use this approximation for model selection. And so we want to figure out whether this is a good thing to do, or if the answers we're getting differ drastically from what we would have gotten had we just performed cross-validation. In fact, a couple of the papers cited stated that this is probably one of the more important directions of future work. So this was, having seen that, that's where we wanted to take this work. Just actually looking at the optimization comparison lemma we had introduced, it became actually rather straightforward for how to get model selection guarantees. So the theorem we were able to introduce informally stated is the following. So if we have two models, one found by cross-validation and the other found by approximate cross-validation, then roughly under the same assumptions, you can ensure that these two models will be on the order of 1 on n close. So this guarantee also certifies that approximating cross-validation will, in this way, actually gives you models that are close, and therefore it can be used in practice. So I actually want to give you a precise example for how these things perform. You know, we have a lot of theorems, and that's really great, but how does this do in practice? This plot was introduced by Tamara Broderick and Will Stevens' work. And the objective here is this L1 regularized logistic loss function. And so in the green, we have this approximation of cross-validation, which uses this leave one out objective, and one that uses just this full Hessian. So the one in blue is actually cheaper, but it seems to not work as well as the one in green. And as you move to even smaller values of lambda, both approximations don't work. So this was pointed to in their paper. And the reason why that was conjectured is the fact that the regularizer is not smooth. So all those guarantees were for settings in which your objective function is twice differentiable, smooth, everything's nice. But as soon as you kind of move out of these settings, then these approximations don't fare as well. So one problem we thought would be very interesting is there approximation to cross-validation that works for non-smooth settings, just as a start? I mean, you want to pipeline these things up to perhaps neural networks or more intricate settings, non-convex losses, but I think non-smoothness is the first thing to tackle. And it's putting your optimization hat on, it becomes quite straightforward what could possibly work in this setting, which is essentially, instead of taking a Newton step, taking a proximal Newton steps. The idea is you optimize a second order Taylor approximation to the smooth part, the loss, and then you perform a proximal step for this non-smooth part. And in many settings, this will be cheaper than if you simply re-optimize the objective function n times. And so again, you can use the approximation to the Hessian that uses a full loss, or you can do a leave one out and loss and then have to compute it in times. So either one will work. And here we're really relying on state-of-the-art solvers that have been designed to solve proximal Newton steps very, very quickly. So GLMNet is one, and then Quick is another package that is commercially available for sparse covariance approximation. So we performed a couple experiments using these packages, and the plot on the left is going to be speed, and the plot on the right is the error that we get. And so this is comparing cross-validation to our proposed approximate cross-validation for this regularized, non-smooth regularized problem. And we found that at least for this standard graphical lasso objective, the speed up's more on the order of 20. So we could perform these proximal Newton steps very, very quickly using Quick. And the relative error was all within 2%. So they were getting really nice empirical guarantees for how well our solutions are going to mirror what the test error does. And again, we took the code for the problem that they cited, and we plotted the proximal, or computed the approximate cross-validation, and this tracked the cross-validation error extremely well, which in turn tracked the test error for the synthetic example well. So this seems to work quite well in settings where you have non-smoothness of the regularizer, which is a much larger class of machine learning objectives. And so then you turn, can we just use the same kind of machinery and get model selection guarantees? And actually, it turns out, no. We could even produce an example which illustrated that if you use this approximation cross-validation, then for the purposes of model selection, you cannot get tighter than a statistical error level of closeness to what you would have gotten had you used cross-validation. So this was a little bit of a disappointment and really left over kind of this new open question of, if I really care about model selection for non-smooth regularized problems, is there a way to do cross-validation quicker? And kind of more abstractly, can we do this for non-convex, or are all these assumptions actually needed, either in practice or theoretically? And so just to summarize, we left our work off at we've provided some sharp guarantees for approximating cross-validation, and more importantly, try to take a step in addressing this problem with non-smoothness. But I think there are more grander problems and in future directions. So that when the dimension is much, much higher than the number of data points you see, a lot of these approximations do not work well. And so there's this question of, how do you do this for this specific setting? I think there are certain structured problems where you can show that this approximation, or adapt the approximation in certain ways that'll kind of fit that setting. But this is very much an open direction. And again, the goal is to extend this class of techniques to non-smooth and non-convex problems, like the ones we see in practice. And so there's some initial thoughts, but this is kind of the frontier where we're trying to engage with. Okay, so before I do a quick summary of the last part of this talk, which will be my toe dip into the fairness space, I'll pause here and take questions and give you a bathroom break or something along these lines. Okay, great. Okay, so the last part of this talk will be some fairness stuff that I've started to wade into. And this will be tackling this problem of kind of setting the appropriate context for these machine learning problems in certain situations, and then studying what are the fairness implications of using machine learning for these settings. When I stepped into the fairness space, I started Microsoft Research New England. There are a lot of fairness people there and a lot of social scientists. And something I kind of got from them is maybe there's this spectrum of problems that seem amenable to very straightforward problem formulations of this type. And then there's another set of problems that aren't. And I think the spectrum is based on how much we can agree on what the correct formulation is. So for games, this is a very structured problem where we all agree on what it means to win and lose and what the state space is. So it's quite no surprise that this is where the success is, the non-controversial success of machine learning lies. But then there are these other applications where, imaging, where there are kind of these spaces where there is some disagreement. So for example, if the image is of me, I have a stake in how I get labeled. And so how you label me and how I would label me might differ. And this might cause some sort of controversy. So to what extent should I be defer to how I get labeled? And this, of course, gets into privacy concerns and what have you. And then there are medical applications. I think there are a lot of resource constraint problems. And so how should we make these decisions in the context of trade-offs? I think there are a lot of people who would disagree about how we should do that in any given setting. And then there are these class of problems where it's just kind of really unclear how we should formulate the problem in the first place. Given we're allocating all these precious resources to people, there's a lot of disagreement and discord, and so it becomes really, really hard to say. So I wanted to paint that context because another really, really hard thing about, I would say, the latter parts of these problems as they interface with people is the fact that there is this kind of feedback mechanism that arises often in these situations. So on the one hand, we're using machine learning to allocate this, opportunities and resources to people. And on the other hand, people are responding to these machine learning algorithms, perhaps by strategic manipulation or just simply altering their behavior to gain access to these opportunities. So they're having kind of this distortion which affects future data. And so you can kind of view this as a dynamical system, trying to understand the effects of machine learning in this way. And so that's actually what we tried to do. And in fact, we started with a model that looked at it, precisely this kind of problem. It's pretty popular in the economics field. So it's kind of led a little foray into the economic space. The model is as follows. So we have an educational institution, and they've admitted some certain people. They have people in their institution. And let's say they've, based on whatever criterion they have labeled people as skilled or non-skilled. And so roughly you could say maybe they're designing an admissions policy if they're using machine learning based on this labeling. And then using this admissions policy, they're allocating opportunities, admissions chances to an oncoming class. This admissions policy, on the other hand, might prompt the incoming population to alter their features to the extent to which they can. And this will feed back into the machine learning algorithm. So this education model in particular was looking at the effect of an affirmative action policy and what kind of incentives it would cause people, or what kind of incentives it would inspire for people to manipulate their features. So people might manipulate their features or change their features in a certain way. This will change the data. This will then change the admissions policy. And so you can think through how this might actually have impacts over the overall population over time. So you're thinking about, okay, if this dynamic is happening, is there an equilibria? And if so, what kind of class will we see at equilibrium in this institution? Okay, so this is the set of motivating questions we had. So what kind of equilibria, and can we think through how we kind of classify these equilibria in terms of maybe fairness or balance across populations? I suggestively labeled these two populations as pink and blue, but of course, there are any number of populations one can study. So when we were looking at previous work, there's a great body of literature thinking through strategic manipulation. And so this is actually closely related to that, but it's a little bit different. So the algorithm, we're actually thinking of people responding to this algorithm as not necessarily making a decision to strategically manipulate their features. This is changing their features in a way that doesn't actually have advantage from the perspective of the institution, but simply just to gain their way into the institution. Here we're thinking of admissions policies as incentivizing actual investments into skill attainment. And then also conversely, if the algorithm is making mistakes and failing to reward certain populations, it might have a disincentivizing effect for people to invest in skills. And so one of the studies, there's a couple studies on this for geographic populations. So when institutions admit fewer people, it causes people to, one effect of this is people might send fewer applications for admission into this place. So there is a discouraging effect when people are not represented in the institution. We're looking at kind of this, exactly this phenomenon, where we're looking at how different groups respond to educational decision policies. Okay, so specifically, what is the model we're actually studying? So this is kind of the model that, this is exactly the model that Coate and Laurie proposed. So there's an institution, it's making decisions based on this equation here, which is trying to maximize this true positive rate and being penalized for false positives. Individuals, on the other hand, are also making decisions based on the policy. So they're making a decision to acquire skills if doing so would cause them a benefit that would outweigh the cost to obtaining the skills. So we assume that every individual has a cost for a skill attainment, and the benefit is based on this wage or future projected wage they would get had they attained the skill. So both the institution and the individual is doing this cost-benefit analysis. And the only tweak to the model that we have is essentially we are making this cost-benefit analysis this individuals are doing. They're also incorporating how everybody else who belongs to their group is doing. So if this false positive rate is high for people who belong to their group, then this is going to have more of a discouraging effect for them than for people who have a nice false positive rate. So this is the model we study, and we have a couple takeaways actually with this model. So one takeaway studying this model was the following. One thing that ensured good equilibria actually across a wide variety of models is essentially if the algorithm makes no mistakes. So there's this burgeoning literature in the fairness space that says complicated models aren't really bad if the error rates are extremely low. And this was actually consistent with that. In the setting where there's really no mistakes or very few mistakes being made, essentially all the groups can be said to be maximally qualified at equilibria. There are very few differences between the groups. Sorry. And so this is just really the ideal setting. However, I think outside of the setting, which is obviously more realistic because algorithms typically always make mistakes in social situations, we found that fairness can be hard. And so here's an example, kind of this toy example that really illustrated our results. So let's suppose there exists a zero error policy for both groups, but not for both groups individually, but not for the entire groups. So for this example here, I can separate the non-qualified and qualified blue people. I can also separate the qualified and non-qualified pink people, but there exists no linear classifier. So here I'm restricting my class of decision functions that can actually separate both groups all at once. So for this situation, there exists two kinds of equilibria. The stable equilibria will essentially benefit one group or the other. So it will always tend to either kind of get a zero error on one group or a zero error on the other. There exists an unstable equilibria, however, and it does this desirable thing, which is trades off on the errors for both groups. But this is unstable in the sense in which if you don't start there for your decision policy, you'll never converge there. So as soon as you start epsilon away from this decision boundary, you'll either favor one group or the other, depending on where you start. And so this is kind of a discouraging thing, which is that you almost never converge these long-term balance equilibria, even if you start close to one. And so in certain situations, if you adhere to these dynamics, fairness might be close to impossible if fairness constitutes balance across groups. We also had some other high-level takeaways. This will be like kind of the ending summary of this beginning work, and I'll tell you where plan to take this, or I think it can be useful. So we studied a bunch of interventions here. So there have been a lot of interventions proposed in the fairness criterion about balancing certain error rates, doing classifiers for each group separately. And so we looked at a lot of these. And we found that a lot of the interventions that worked in the static setting really no longer work in this dynamic setting. And so I think this was meant to be a catalyst for people in the fairness space to really think more about how fairness interventions can be helpful, more long-term dynamic situations, and really kind of try and think through how you can incorporate how users might be responding and thinking through decision policies or machine learning policies. In this model, one thing that really did help equilibria across the board is subsidizing the disadvantaged group. So everyone's doing this cost benefit analysis. If you lower the costs for everyone, particularly for groups for which the cost is higher, then the equilibria tended to both theoretically and empirically just be better. So, I mean, but that's an intervention very much tailored to the model. Although empirically, I think Raj Chetty and people have actually seen beneficial effects to subsidies. So put that what you may. But yeah, this is, as I said, meant to be a catalyst looking at this. I think this is actually the setting in which a lot of algorithms ought to be studied that interact with people. And so we're still trying to develop more principled ways of viewing our understanding feedback, hopefully with more flexible models or models that mirror very particular situations a little bit better. So just a summary, as I mentioned, dynamic models are kind of very important. I'm hosting a NeurIPS workshop on dynamic decision making, so hopefully some of you guys can attend. But as we go forward, I mean, this was a game theoretic point of view, and so drawing that connection, I actually think more refined in a more refined manner would actually give us more sharp guarantees. I'm also trying to collaborate with people, social scientists who work in specific spaces to get more accurate models, use kind of these studies to really get better models for how people do react to certain algorithmic decision making. And so I think that this will be beneficial moving forward. So with that, I'll end and I will take questions. Thank you so much for your attention.
Thank you for the great talk, Ashia.
Thanks.
Well, I'll clap on behalf of everyone.
Okay, great.
So yeah, if you have a question, please feel free to directly unmute yourself and ask now. Oh, Sandesh has a question. Would you like to ask your question?
Okay. So my question is about the last figure, last conclusion that you showed that fairness can be hard. So my question is, can you reformulate the problem so that your objective is to find the features? By taking those features, you would reach an equilibrium which is fair and stable. So, so in your figure, you are, for example, the X and Y axis represent some features with respect to which those dots are classified.
Yeah.
But like, isn't your objective should be defined in such a way that you should find the features or the data points should be coded in such a way that once you use those features, you reach an equilibrium that is both stable and fair.
Yeah, I think that's true. So we were looking just simply where the machine learning algorithm just naively does kind of a cost minimization. So if we had tweaked the objective function that the machine learning algorithm was using, I'm pretty sure we could break out of this situation, although there were several other kind of pathological examples we could derive for various fairness proposals that have been made. So if you try to equalize the odds, we could propose a situation where you would also get into a pathological situation. So it's not quite clear, unless you understand the situation beforehand, it's really hard to design these algorithms to kind of break out of this pathological behavior. I hope that kind of makes sense, but I guess the point we were trying to make is in dynamic models, it becomes extremely hard unless you have a very well-defined description of how people are responding to get out of these situations where you find equilibria, well, one where equilibria exists in the first place. We had a bunch of situations where that didn't happen. There were like limit cycles, and then where we could get out of pathological ones. So this was a very kind of complicated model to study, but I have no doubt that for this specific example, what you propose would work.
Okay.
I have a question.
Yeah.
You had mentioned in the very beginning kind of this perspective that like that there's a spectrum of problems that go from, you know, problems where everyone agrees what the objectives are to problems where, you know, where it's more controversial. I mean, but the work that you're presenting here, even in order to label who's correctly
skilled and non-skilled, yeah,
that's kind of assuming that that label itself is you know, that there is some objective truth answer. Is there, what could be done in the case when, how do people formulate when there is not an objective true answer and you can't actually grade, and in that sense there's no notion of like perfect accuracy, even if you had like a, you know, yeah. I mean, I guess there wouldn't even be a way of defining what do you mean by,
I think it's an active debate in the fairness space. From what I can tell, I'm actually a little more of a novice in this space, so I'm sure somebody in the audience might actually have a better answer for what has been proposed to deal with the fact that even just labeling is kind of a matter of subjective opinion, and it becomes hard to agree upon this, and can have distortions for what outcome you end up with. In some sense, the reason why I put that chart there in the first place was because I presented this work to some social scientists, and they were like, you need to, you know, put some context behind your labeling of skilled and unskilled. And really, have several caveats there, because that is highly controversial. So that's definitely questionable. But even if you could agree, I guess this was supposed to be a separate problem. If you could agree, there's still problems when you have feedback.
Are there any further questions for Aisha?
All right, well, thanks everyone for your attention. I really appreciate it.
Well, thank you, Aisha, for the great talk. We really enjoyed it. And on behalf of the SNAPP seminar organizers, I'd like to thank all of our speakers this fall semester. All the talks were amazing. We had an amazing lineup of speakers, and we're really looking forward to the spring semester series as well. I also want to thank all of you participants and audience for attending the seminar series and making the series great and having a lot of good feedback. So we will be announcing the speakers for the spring seminar on our website soon. And as a reminder, we will be taking a break from the seminar series after today's talk, and we will reconvene and restart the seminar series on January 25th. Well, thanks everyone for being here, and we'll look forward to seeing you in the spring.
Bye everyone, thanks again.
Bye, thank you, Ashia.